In example 7, we're finding the domain of a radical function composed with a rational function. So we want to find the domain of the function f of x, which is equal to the square root of x plus 2 times x minus 3 over x minus 1. Now, because a square root is only defined when the quantity under the radical is non-negative, we need to determine where this rational function x plus 2 times x minus 3 over x minus 1 is going to be greater than or equal to 0. Now, the output of a rational function can change signs, change from positive to negative or vice versa, at x-intercepts and at vertical asymptotes. For this equation, the graph could change signs at x is equal to negative 2, 1, and 3. Now, to determine the intervals on which the rational expression is positive, we could test some values in the expression or sketch a graph. While both approaches work equally well, for this example we're going to use a graph as shown in figure 9. So here you have your function. We have the vertical asymptote at x equals 1. We have x-intercepts at negative 2, 0, and then positive 3, 0. And so we want to figure out where are the outputs that are non-negative. So this function has two x-intercepts like we stated, both of which exhibit linear behavior near the x-intercepts. There is one vertical asymptote corresponding to a linear factor, and this behavior is similar to the basic reciprocal toolkit function. And there is no horizontal asymptote because the degree of the numerator is larger than the degree of the denominator, and there is a y-intercept at 0, square root of 6. Now, from the y-intercept and from the x-intercept at negative 2, we can sketch the left side of the graph. And from the behavior at the asymptote, we can sketch the right side of the graph. Now, from the graph, we can now tell on which intervals the outputs will be non-negative, so that we can be sure that the original function will be defined. F of x is going to have the domain where x is in between negative 2 and 1, or x is greater than or equal to 3, or in interval notation, negative 2, 1, union, bracket 3, infinity. Now, if we don't want to do this by graphing, then we can do the following. We can look at the function under the radical, which is greater than or equal to 0. And so that's when we want to know when it's greater than or equal to 0, because it doesn't matter that whatever is underneath the radical sign, it has to also be greater than or equal to 0. So in the past, what we would do for this rational function is we'd find the boundary points. Well, the boundary points are in the numerator. So x is equal to negative 2 and x is equal to positive 3. And then we also have to use a boundary point where the vertical asymptote is x is equal to 1. So we have our boundary points at negative 2, 1, and then 3. So now, before we figure out anything else, we need to figure out what is the interval for each before we start trying to figure out which one is true and which one is false. So the interval that goes from negative infinity to negative 2 is going to be parentheses negative infinity, negative 2 with a bracket. The reason why it's a bracket is because it's greater than or equal to, and the value of negative 2 as a boundary point is in the numerator. For the second interval, it goes from negative 2 to 1. So again, we're still including negative 2 in the numerator, but the value of 1 has to be a parenthesis because it's a vertical asymptote. And that means that when you plug 1 in for x, it's going to make the denominator 0 and undefined. So that's why you have a parenthesis at 1. And then in between 1 and 3, we have parenthesis 1, 3. And again, 3 is in the numerator, so therefore you're going to have a bracket there. And then from region 4, you're going to go from 3 to positive infinity, including the value of 3. And then what we would do is we would check and test a point from each of these regions. So for region 1, we plug in negative 3. Plug it into the rational function, we would get a negative value, which is not greater than or equal to 0, so it would be false. In region 2, we can pick the 0 value since that's the easiest. When we plug in 0, we get a positive number, 6, which is greater than or equal to 0. So therefore, it's true in region 2. For example, for region number 3, we can plug in the number between 1 and 3, which is 2. And what we end up getting is a negative value, which is not greater than or equal to 0. So therefore, it's false for region 3. For region 4, we can pick a value 4 and plug it in. And so we get up a positive result, which can be greater than or equal to 0, which is true. So it's true for regions 2 and 4, and those were the interval notation for those. So we would get bracket -2, comma 1 parenthesis, union bracket 3, comma infinity, and we can see that it matches what we got for our solution by looking at the graph. So either or is okay in how you want to go about that.